Hello and welcome. I'm going to speak about the energy aspects of artificial intelligence. This lecture is the English version of the original lecture presented at the Technion on December 28th, 2025, which I gave with the invitation of Ignite the Spark group of students, T-Hub, and the sustainability program of the Technion University. I'm going to cover the artificial intelligence topic from my experience as a professional in the energy sector for the past 15 years. So my name is Ben Kraversky, and I'm a master's, which I obtained from the Tel Aviv University in the field of nanotechnology. Over the past 15 years, I've consulted and worked in the international arena for most of the time. I've taken part in 4 ventures of energy innovation, and I'm also working with various companies from across the globe and also in Israel. I will mainly speak from my position as the founder and currently the director of Soltell Systems, which is the data analytics company established in 2019. And I'm also the country representative of Aleasoft Energy Forecasting, a European company, which is also operating in Israel, providing state-of-the-art hybrid models for energy forecasting in terms of demand and prices, and utilizing, of course, artificial intelligence for this purpose. So I want to start with some headlines from the media today. And for example, we are talking about significant change, which is ongoing in different aspects of life, mainly in the business, but some think it's something even more profound. And of course, you probably know that it all started with the advent of LLMs, the large language models, about 3 years ago. But we have to understand also that artificial intelligence is a phenomenon which has not begun 3 years ago. It's something a little bit older. But on the other hand, LLMs allowed this to be exposed to the general public. So everyone can use artificial intelligence today, and it's not something which is strictly in the professional domain. We also hear that artificial intelligence is going to interact with energy quite a lot. We hear these headlines that electricity demand is going to jump because of the use of artificial intelligence, which is an energy demanding topic. And it also has effects on automation. So there is fear of massive layoffs, which have not yet realized. But on the other hand, we do see an effect on the job market. That's undeniable. We also see geographic shifts. So China versus United States versus Europe all try to be leaders in the AI. And of course, we see private companies, major ones in the IT sector, changing their focus suddenly to the energy domain because of their involvement in data centers, obviously. And of course, we also see using artificial intelligence for energy optimization, on the other hand, which is a good thing. So we see a lot of things related to the energy domain, and I will try to make some order in this. So I want to go back to 1998, and back then I was a high school student, and we had a course in high school which was called artificial intelligence. And back then we were utilizing a language, a programming language called Prolog. Prolog is a high-level logic and declarative language, and it was used for basically defining decision trees. And at the time, it was artificial intelligence. So, of course, the definitions changed over the past almost 30 years, but we see that the use of the concept of artificial intelligence is quite veteran, I would say. So I want to make some clarifications. So statistical regression and statistical models are not generally defined as being artificial intelligence. I think this is pretty clear. Decision trees, which at the time in the 90s, some defined them as artificial intelligence, today are not generally considered to be artificial intelligence, but rather straightforward models for decision making. Machine learning, which is something which is also not new, it is still defined by many as artificial intelligence, but finding patterns and making decisions is sitting probably right on the border between conventional data science and artificial intelligence. So only when we go to deep learning, which is also including learning patterns and allowing to make complex decisions, we can truly speak about artificial intelligence. And of course, the most recent advent of LLMs, the large language models, which enable processing, understanding, and communicating in human understood language, this is indeed artificial intelligence. And there are, of course, more complex things which are being developed right now in this domain as well. I mean, I'm not going to talk about them because they're not yet commercial, I would say. They're just mostly in research phase. So I found this excellent chart, which is describing pretty well the difference between traditional data and business intelligence and the further more complex topics of data science. So in this sense, traditional and big data is mainly dealing with data itself, like ordering it, filtering it, managing it. In business intelligence, we're speaking about visualizing the data and making conclusions typically by human operators. But further, if we go to the next step, traditional data science methods, which are also including regression and clustering and factor analysis, they are allowing automations, but still not being part of the artificial intelligence domain. And then when we move to machine learning, we are beginning to touch artificial intelligence, especially when we go from supervising and unsupervising learning to deep learning and further. So in this sense, I would place, for example, Soltell systems. It's mainly dealing in the traditional methods of data science and a little bit touching machine learning. While, for example, Aleasoft Energy Forecasting is sitting strictly in ML and deep learning, dealing with neural networks, which is NNs. And those neural networks are essentially utilized to improve the prediction accuracy of their models. So let's look again. I spoke about machine learning. I spoke about deep learning, neural networks, which is part of the deep learning concept. And if we go further, we also see large language models, which are, of course, something we know today from everyday life on the internet. It's basically now found everywhere. So I want to focus on solving real problems in energy. So machine learning is something, as I mentioned, which is not new. Machine learning actually began to be utilized already in the 1980s. Originally, it was for exploration, production of hydrocarbons, and quickly professionals started utilizing it for forecasting demand and supply of energy, to manage energy, to make grid optimizations, and if we look farther into the future, people began utilizing it for energy trading, for making fast automated decisions. So we are speaking about essentially something which began in the 80s, but we see a significant growth over the past 10 years, and especially in the past, I would say, 5 years, we see a lot of utilization of machine learning and deep learning, reinforcement learning. So this is something which has become pretty much part of the energy landscape. And at this point, let's look at two examples from my professional experience. So when artificial intelligence is a must-have, which is an enablement technology, and when I would later speak about when artificial intelligence is mostly an optimization technology. So for example, in forecasting electricity prices, Aleasoft are utilizing a hybrid model. So there are statistical and econometric models, there is machine learning, and the hybrid is utilizing both of them. So this is something Aleasoft is doing. And specifically, I will show you long-term electricity price forecast, which was generated in October 2010 for the Spanish market. And you can see that the black line, which is the real price, is falling pretty much in the forecasted threshold, except the big energy crisis in Europe in 2022. Because of the geopolitical situation, which was a little bit of a black swan. So artificial intelligence cannot really predict things, but it can make forecasting better. Now, for the long-term electricity price forecast, it's not mandatory to utilize AI. It's just improving the forecast. But on the other hand, if we move to short-term electricity price forecast, which is for the next few hours or days, this is something where artificial intelligence is becoming a must, okay? So for the long term, it's optimization. For the short term, it's a must. You cannot do good predictions without utilizing AI, which is fastly adapting to the changes in the electricity prices. So that's the chart I was speaking of, the electricity price forecast for the Spanish market. And you can see that it's falling pretty much well inside the range, the predicted range, except this 2022 crisis. And as we see that actually this month, the price forecasted some 15, 16 years ago is exactly the price which we see in the market, which is pretty amazing, I would say. Another example, I will speak about optimization utilizing AI, and I will look at it from another perspective. I will look at measuring soiling in photovoltaic plants. So there are actually three available methods to do so. One is hardware soiling sensors, which is pretty straightforward. You just put a soiling sensor, which is a light induced sensor, which is being cleansed all the time, and you're basically measuring the difference between the reference sensor and the solar plant. Another method is utilizing machine learning, for example, by a company named Aleasoft in the United States. This is working as well. There are, of course, differences. And Soltell system pioneered another method, which is not relying on machine learning, but on an industrial IoT technology called sensorless. And you can see, for example, here that we see a plant being cleaned from dust. And in this case, Soltell measured it, and it was determined to reduce 12% of power from the plant. And this was one of the triggers to make the cleaning of the plant. So this was done without machine learning. And actually, we have very good results without utilizing artificial intelligence, even though we could, but we don't see a significant advantage there. So that's how cleaned and non-cleaned systems look in terms of soiling. You can see that soiling accumulation is reducing output pretty much linearly, I would say. And those systems in blue and green, those are systems which are clean and being measured with sensorless technology. So here you can see that the yellow one is accumulating dust and being cleaned. This test was performed about 5.5 years ago. Excuse me, even a little bit less. Okay, so enablement versus optimization. That's the thing with AI in the energy domain. And if we classify the different topics in the energy domain, I would say that in terms of asset planning and forecast optimization, we do see that this is mainly an optimization topic. And the effect is not substantial, okay? So for example, for long-term forecasting, the effect is not, it's better, but it's not dramatic, okay? On the other hand, if we move to predictive maintenance and energy management, so the effect is more significant, more notable, but we're still dealing with optimization. It can also work, for example, energy management can also work with predetermined algorithms and predictive maintenance as well. But with machine learning, we can make things a little bit better. On the other side of this square, we can also find, for example, energy advisory with LLMs mostly. And energy advisory, of course, it's something which is not possible without LLMs. But on the other hand, the value of it is not substantial, typically, because AI is still not really replacing human expertise in such complex topic like energy. Where we see a true enablement of AI technologies combined with a true incremental impact of those technologies, this is real-time energy trading. So machine learning enables real-time decisions there, which are not really possible to be made by humans. And of course, autonomous grid operations, which is also requiring very fast response in a matter of seconds. So humans cannot really do that. And this is where the impact of AI technologies is really significant. And from here, I think it's a good point to talk about what's the impact of a surge in AI utilization on electricity demand. So there is a lot of talk about it, and I want to put it into perspective. I want to understand and to show you how much energy indeed is required, how much energy is going to be required in the future, and what are the possible solutions for that. So first of all, today we see utilization of about 450 terawatt hours of electricity for data centers, correct, for 2025. This chart is by the International Energy Agency, and they forecast a surge to over 800 terawatt hours per year by 2030. And again, this is only data centers, and this is not only AI. AI is only a certain part of it, about a dozen% as of today, and it's going to increase in the future. So one of the main drivers of the increase from about 450 today to about over 800 in 2030, this is coming from indeed from AI. But even in 2030, AI is not going to be the most of the data center processing demand, okay? But it's going to be a very significant one, okay? Now, first of all, what can power the fast deployment of data centers? So we need to build basically a chunk of data centers, which is about the chunk which we have today active. So we have to double it in about 4 to 5 years. And a lot of talk is about nuclear and even about hydrogen. And I will refer to those as possible solutions. But I think the most relevant ones are actually natural gas and solar and storage, because they allow a much faster deployment, and they are more modular, I would say, to be deployed near the sites of potential data centers. If we look at the time to build nuclear, we're speaking about very, very long timelines, which is at best 7 to 10 years. But in reality, especially in the West, we see projects which are ongoing for 20 years, even more. So that's not really realistic. There are SMRs, which are small modular reactors, but we have to understand that as of today, there is only one active SMR in the world, and hence this technology is not really commercial available yet. It's a promise to shorten the time for deployment of nuclear power to a few years, from 10, 20 years, but it's not yet there. So for the next 4 to 5 years, SMRs are probably not going to solve the problem. Hydrogen is not so much relevant as well. So if we talk about hydrogen, of course, we talk about fuel cells. So fuel cells is a mature technology, but hydrogen infrastructure is not really available to deliver it to multiple sites. And this technology is developing very slowly, so I don't think it's relevant for deployment of data centers. On the other hand, natural gas is much more relevant to this short time frame. It could get deployed within just 3 years. I'm talking about gas turbines and gas infrastructure as well. So in places where you already have a nearby gas infrastructure, it's not a big challenge to put turbines there and deploy data centers. This is something which is feasible. And of course, solar and storage. Today, it's the fastest and the cheapest way to deploy energy. It's very modular, and you could put it anywhere in the world, in the Sun Belt, okay? The negative side of solar and storage, that it's not really available 100% of the time. It's less available in terms of a constant supply of natural gas. So you still have to connect it to the grid. It cannot be an off-grid solution, not yet anyway. Another aspect of AI deployment is the bottleneck. So first of all, if we deploy the data centers and connect them to electricity, that's one side of the challenge. The other side is that we also have to connect it to the network, and this is another aspect of infrastructure. So today, for example, we typically build data centers in clusters. So you have one in Virginia, in the US, in Ohio, and in Ireland, in Europe. But we see there is a tendency to make data centers more distributed across the world. And in order to do so, we need to connect them to high bandwidth networks in order to enable them to provide the required services. And this is another part of the challenge. If we look at AI, so today, for example, AI is about 5% of the network communication. It's not really taking over yet, but in the future, if we're talking about 2030, it's already going to be close to something like 20% of the network communication capacity. So in 2025, communication through the internet grew by 19%, and AI is among the growth factors, but it's still not a dominant factor. It is going to become more dominant in the future. By the way, today the most demanding aspect of the internet communication, which is taking most of the bandwidth, is video. It's taking most of the capacity. So we see with this growth, and we see the demand, but there are actually solutions which can make this deployment much easier. So one of the solutions which we see is was published just in the last month of 2025, and this is the Google model called Gamma, which enables running an LLM model on the processor of a cellular phone. So they claim that the processor of the cellular phone, of the smartphone, can actually answer about 4 out of 5 queries which we generally make with AI, with the LLM. And effectively, this means that the smartphone can process locally 80% of the AI demand. So you don't need to utilize the network, and you don't need the actual electricity. And how much electricity does it need from your cell phone battery? It's actually not much. It's just 0.75% for 25 queries. That's not much at all. So a big part of projected demand can actually be answered with localized processing instead of giving the data centers the responsibility to process every query. Another aspect, before I finalize my talk, is the cheap energy consumption. So this is connected also, of course, to the data centers, as well as to the processors of smartphones. We do see improvement in chips, and not just improvement in their processing ability, but also in their energy demand. And if we look at the trend, we see an exponential improvement in energy demand of processors. So again, we do require more data centers in the future, but they are going to be built with better processors which require less energy. And it means that instead of building twice the capacity of current data centers and hence demanding double the electricity, we will need essentially less electricity, and which is a good thing. So I think combined with localized processing, we can see that the problem of both electricity demand surge and the requirement for more network capacity is not that problematic in the next few years. And from here, I think let's look at the general situation. How much AI is impacting the market from the perspective of jobs, which is I think, most interesting to many students. So, in my opinion, AI is going to affect some segments of the job market, and we can see that already. Some jobs can be automated substantially. We're talking about fields like finance, software development, content creation, law, and in the farther horizon, we're also talking about transportation, autonomous driving. So those are the segments which are going to be significantly affected. But overall, the energy segment, if we, of course, put transportation on the side, which is also related to energy to some degree, but if we look at the energy segment, the effect is not that substantial in terms of jobs. So today we're speaking about 77 million people being employed in energy, which is going even to rise, according to most projections, to about 80 million by 2030. In general, if we look at what's happening in the energy market, so energy transition and renewables is driving more demand in jobs, and fossil fuel is on decline, and hence we see a decline in associated fossil fuel jobs. In automation, we see an effect, of course, which is making a reduction in some energy jobs, mainly the ones which can be easily automated, like office and monitoring, things of this kind. But on the other hand, introduction of more AI systems and IT, especially together with renewable energy, also puts more jobs on the market, which is a good thing. Overall, I think we have to take it into some context. So if we look at developed countries, most of the countries are experiencing a demographic decline, and we actually see more demand in energy jobs when there are people available to fill the jobs. So in this sense, automation is actually a good thing for the energy segment overall. And I think AI is a positive thing in the next few years, which will enable to cut a substantial amount of jobs while creating many other jobs instead, which are more sophisticated. And this is what we are going to see. I think, in my opinion, in developed countries, the situation is probably going to be different in the third world. So let me summarize. So we are going to see about 9 million new jobs related to energy transition, mainly renewable energy and energy management. We're going to see reduction of 2.5 million jobs in fossil fuels. There is also positive aspects of artificial intelligence, reducing emissions and optimization of energy trade, where it is an enablement technology. We're going to see twice many electricity demand by data centers, at most, I think, maybe even less because of the technology advancement I've mentioned. And of course, we are going to see a reduction of 3 million jobs in the energy market because of automation, but overall, it's a net increase, probably. Energy efficiency is going to drive actually a decrease in electricity use by 0.5%. And overall, data centers are going to rise from about 1.5% electricity demand today. I think the AI future is very exciting. And of course, my AI assistant advised me to invest into this field. And of course, I utilized LLM also to prepare this presentation. And I think that's pretty standard today. So indeed, we see the artificial intelligence technology entering the everyday aspects of our lives. So hopefully it was interesting, and goodbye.